the last week, we defined the notion of complex differentiability. We saw that complex differentiable functions also satisfy the laws of calculus, namely linearity, the product rule, quotient rule, and also the chain rule. Thereafter, we saw a few examples of complex differentiable functions, and in particular, we noted that polynomials in the variable z are complex differentiable in the entire complex plane. They are entire functions. This week, we begin by discussing the notion of power series. Power series is an infinite degree variant of a polynomial. Inside its disk of convergence, a power series behaves very similar to polynomials, both analytically and algebraically. Let's start this lecture by defining a power series around a point z0 in the complex plane. Power series. Let z0 be a point in the complex plane, a formal power series around z0 with complex coefficients. Is a formal expression summation an z minus z0 to the power n, where the sum is from 0 to infinity, where an are complex numbers. And z is an indeterminate. So this is a formal power series. The z featuring in the expression of the formal power series is an indeterminate. We could ask about the convergence of this power series for a complex number z. For z in C, we could ask whether the series of the complex numbers, say summation a n z minus z0 to the power n, converges or not. So we could ask whether a formal power series converges at a given complex number, given point z in C. So for example, at the point z0, the power series around z0. So this is power series around z0. I have written it. So a power series around z0 will always converge at the point z0. Absolutely. At z0, the formal power series converges absolutely. The formal power series given by summation a n z minus z0 to the power n converges absolutely. Another example would be to consider the geometric series summation z to the power n. If I don't write the limits, it's understood that it is from 0 to infinity. So if you consider the geometric power series z to the power n, then for mod z greater than or equal to 1, take any point z which satisfies mod z greater than or equal to 1. The summons mod z to the power n, mod z to the power n is just mod z to the power n is greater than 1 and does not converge to 0. But if the series of complex numbers summation z to the power n should converge, it's forced that the summands converge to 0, right? And because the summands here don't converge to 0, This series does not converge. Hence, summation z to the power n does not converge or it diverges. So it's a question of interest to check at what points a given formal power series converges and at what points the formal power series does not converge. The question is answered by studying what is called as the radius of convergence of the given power series. So let me just define that. Radius of convergence. This is given a power series, we can talk about the radius of convergence. Let summation an z minus z0 to the power n be a formal power series around z0. We define the radius of convergence R of the formal power series to be the number in 0 infinity with both 0 and infinity included, where the number is given by R is the lim inf as n goes to infinity of mod an to the power minus 1 by n. This is exactly how you would have defined a radius of convergence in a course in real analysis when you study real analytic functions. So this is the lim inf as n goes to infinity of the minus of 1 by nth root or 1 by nth root of mod an. The radius of convergence, as the name suggests, is a quantity which tells us something about the convergence of the given formal power series, which is captured in the next proposition which I will be writing. If you notice, the definition of radius of convergence implies that R in some sense captures how the coefficients of our given formal power series decays, how fast and to what number the coefficients decay. The proposition which I will be writing now tells us that if we are in a disk of radius r around z0, the formal power series converges absolutely in that disk. And if we are in the complement of the closed disk of radius r, the series diverges in that region. Let me note that. Let summation an z minus z0 to the power n be a power series around z0. Then for z in dz0 r, okay, let r be the radius of convergence. Let r be the radius of convergence of the formal series, of the power series. Then for z in dz0 r, the series summation an z minus z0 to the power n converges absolutely. Notice that here the z that is featuring in this power series is the complex number z in dz0r. In this case, it was just an indeterminate, so the distinction has started coming in. The proposition, the first part of the proposition says that in this disk of radius r around z0, this is called the disk of convergence. The formal power series, when evaluated at z, converges absolutely. series of complex numbers converges absolutely. For r less than capital R, the series converges uniformly. Can say more, it converges uniformly on dz0 small r. Furthermore, that's not the only thing, we only talked about where it converges. If absolute value of z minus z0 is greater than capital R, then summation an z minus z0 to the power n diverges. So outside the closed disk of radius r, the formal power series when evaluated at any point z, it diverges. So the disk, so let me just note that the disk dz0r is called the disk of convergence of the formal power series. Let's give a proof of this proposition. Okay, let me go over the statement of the proposition once more. If we are in the disk of convergence dz0r, the power series summation a n z minus z0 to the power n converges absolutely. And in a smaller disk, it converges uniformly. Outside the disk of radius r, the series diverges. Let's give a proof. Let's give a proof of what happens when mod of z minus z0 is greater than r. Let mod of z be a point in C such that mod of z minus z0 is greater than capital R. Now, the fact that mod of z minus z0 is greater than capital R and the fact that R is the lim inf of mod a n to the power minus 1 by n tells us that there exist infinitely many natural numbers n such that mod a n to the power minus of 1 by n is less than mod z minus z0. Let's see what happens if that is not the case. If there doesn't exist infinitely many n such that mod a n to the power minus 1 by n is less than mod z minus z0, then after a point mod a n to the power minus 1 by n would be greater than or equal to mod z minus z0, and that would imply that the lim would be greater than or equal to mod z minus z0. But the lim we know is equal to r, which is strictly less than mod z minus z0. Hence, that cannot happen. So there should necessarily exist infinitely many such natural numbers, hence is that mod a n to the power minus 1 by n is less than z minus mod of z minus z0. Okay, this implies the fact that there exist such natural numbers implies that mod a n to the power 1 by n, remember that these are all positive numbers, so I'm freely multiplying to get the inequality mod a n to the power 1 by n z minus z0 to the power n. Z minus z0 is less than, is greater than 1 for infinitely many natural numbers. But then taking power, this implies that mod of a n times z minus z0 to the power n is greater than 1 for infinitely many values n. But what can we say about a series which converges? We know that the summons of the series should converge to 0 if the series is to converge. But we have seen here that there is a sequence of summons which constantly have absolute value greater than 1. Hence, this series cannot converge. Since the summons does not converge to 0, let me call this star to 0 by star, we have we conclude that summation a n z minus z0 to the power n does not converge. So that was quite straightforward. So if mod z minus z0 is greater than capital R, the series does not converge. Let's next explore what happens when z belongs to the disk of radius capital R around z0. Let z be in B z0 capital R. This implies that mod of z minus z0 is less than, say, some small r which is less than capital R for some r greater than 0. But again, let's invoke the fact that capital R is the limit. Since capital R is the lim inf of mod a n to the power minus 1 by n, there exists some natural number n such that for all n greater than capital N, mod a n to the power minus 1 by n is greater than r. Let's see why that is the case. If there is no such n, we would have had an infinitely many n such that mod a n to the power minus of 1 by n is less than or equal to small r. But that would imply that the lim inf is now less than or equal to small r as well. But we know that the lim inf is equal to r, and that small r is strictly less than capital R. And hence this should that would be a contradiction. Hence this should necessarily happen. Right. So what is the implication of this? This is for all n greater than this capital N. Okay, that implies that mod a n r to the power n. Remember that these are all positive numbers. I am freely manipulating the inequality here to conclude that this is less than 1 for all n greater than capital N. All right, now let's assume, let's analyze the tail of our given power series. So look at for n greater than capital N, what is n times z minus z0 to the power n going to behave like? This is exactly equal to a n into r to the power n times mod of z minus z0 to the power n by r to the power n. And we just checked that for n greater than capital N, mod a n times r to the power n is less than. So this is less than or equal to mod of z minus z0 by r to the power capital N. Notice that mod of z minus z0 is less than r, and therefore mod of z minus z0 by r is a number which is less than 1. Therefore the tail summation mod a n z minus z0 to the power n, where n is greater than capital N, is less than or equal to the sum of mod of z minus z0 by r to the power n, which is a geometric series and which we know converges. And therefore, for any z, the absolute, the sequence of absolute, hence summation a n, before capital N there are only finitely many terms, and hence this series converges. That's precisely the definition of a series being absolutely convergent, i.e. summation a n z minus z0 to the power n converges absolutely. In this proof, we have already laid the framework to prove that in a smaller disk, the series converges uniformly. So let's do that. So let R be less than capital R and R1 be such that R is less than R1 is less than capital R. We'll use the same trick now. For there exists some n in natural numbers such that for all n greater than capital N, mod a n to the power minus of 1 by n is strictly greater than R1. Yeah, R1. Instead of smaller, let's now use this. Which in particular is also greater than small r. So if you now consider mod of a n into z minus z0 to the power n, this is equal to mod of a n r1 to the power n times mod of z minus z0 by r1 to the power n. No, there's an n here as well. But then we just know that for n greater than capital 1 and z in d z0 small r is what we are interested in. And because z is in d z0 r, absolute value of z minus z0 is bounded by small r. So this is less than or equal to, this term is bounded by 1 and the other term is bounded by r by r1 to the power n. So since summation r by r1 to the power n from 0 to infinity is a geometric series which converges, is a convergence series because it's a geometric series. Given epsilon positive, there exists capital N such that capital N0, which is greater than capital N, such that summation n greater than or equal to n0 of r by r1 to the power n is less than epsilon. So then what do we have? Then the absolute value of summation a n z minus z0 to the power n, this series which we now know converges in dz0 r, this minus summation n is equal to 0 to the partial sum of a n z minus z0 to the power n, this is precisely equal to the absolute value of n greater than or equal to, maybe n strictly greater than n a n z minus z0 to the power n, which is less than summation absolute value of, the absolute value can be taken inside and we will write this as less than r by r1 to the power n, where n is greater than or equal to n naught. They are all positive numbers, which is less than epsilon. And this does not depend on the point z. So the series converges uniformly on dz0 small r. And that completes the proof of the proposition. So the radius of convergence tells us exactly how the power series converges and diverges. In the disk of radius r, it converges, and outside the closed disk of radius r, it diverges. But many times it's quite complicated to compute the radius of convergence explicitly due to the way it is defined. And there is the ratio test which can be used to approximate our radius of convergence. Let me write that down in the next proposition. Let summation a n z minus z naught to the power n be a formal power series. With radius of convergence r. Further, let's assume that a n is non-zero for n sufficiently large. Then the ratio test tells us that the lim inf n going to infinity of mod an by mod an plus 1, this is less than or equal to r, which is our radius of convergence, which is less than or equal to the lim sub mod an by mod an plus 1. In particular, if the sequence of numbers mod an by mod an plus 1 converges, then the lim inf and the lim sub both are equal, and that would be equal to the radius of convergence. So that will be the ratio test. Let's give a proof of the statement. Let R1 be equal to the lim inf. The strategy we will adopt to prove this proposition would be that if small r is less than capital R1, we will prove that small r is less than or equal to capital R. And that way, it would force capital R1 to be less than or equal to capital R. Let's do that. Let R be less than capital R1. Then by the very definition of lim inf, then there exists a capital N in natural numbers such that for all n greater than capital N, mod of an by mod of an plus 1 is strictly greater than r. Notice that this is forced because if there does not exist one such capital N, then there will be infinitely many values of n such that mod an by mod an plus 1 would be less than equal to r, and that would imply that the lim inf is less than or equal to small r. But then we know that it is equal to capital R1, which is a strictly greater quantity than small r, and hence that cannot happen. We would arrive at a contradiction in that case, and therefore there exists such an n where for all n greater than capital N, mod an by mod an plus 1 is greater than capital R. Let's see now what happens for z in dz0r. We will show that the sequence is for z in dz0 small r, the power series necessarily converges. To do that, let's consider mod an z minus z0 to the power n, where n is greater than capital N, this capital N here above. Suppose we have z in dz0r. This would mean, or rather let's consider an plus 1 and see what happens. An plus 1 z minus z0 to the power n plus 1. This is less than or equal to mod of an plus 1 times r to the power n plus 1 times z minus z0 to the power n plus 1, or let me put it this way, by r to the power n plus 1. This is precisely the meaning of, in fact, I have not done anything, so this is actually equal to the same number. The inequality will come from here next. This actually tells us that mod an plus 1 times r is less than mod an. And this tells us that this is less than mod an times r to the power n into mod of z minus z0 to the power z minus z0 by r to the power n plus 1. And by an induction argument, we can conclude that this is less than mod of a capital N r to the power capital N times absolute value of z minus z0 by r to the power capital N plus 1. Therefore, we have bounded for n greater than capital N all mod an plus 1 times z minus z0 to the power n plus 1. Hence, the tail z minus z0 to the power n, where n is greater than or equal to capital N, the absolute value of this is less than or equal to the some, maybe you can put the mod A capital N R to the power n outside and write this as mod z minus z0 by r to the power n, and n is greater than or equal to capital. Notice that mod z minus z0 by r is less than 1, and this is the tail of the geometric series which converges, and therefore we have this sequence converges. In fact, we have shown that it converges absolutely. But what does that mean? That means that this means that d z0 r is contained in the set of all z such that mod z minus z0 is less than or equal to capital R. Because if you go outside the closed disk of radius r, we know that the series diverges for sure. So this is certainly the case, and that implies that r is less than or equal to capital R. But that's precisely what we wanted. We have shown now that for every r less than r1, r is less than or equal to capital R. Since this is true for all r less than capital R1, we have R1 is less than or equal to capital R. And that's precisely what we had started. This is the inequality that we have just proved. Okay, now let's focus on this inequality. The proof is quite similar. The techniques are, the idea is the same. Let's very quickly look at it. Instead of the convergence, we will now show divergence of the series. Let R2 be the lim sup as n goes to infinity of mod an to the power, mod an by mod an plus 1. We will take some r greater than R2 and let's see what happens for mod z minus z0 greater than R2. And let z in C be such that mod z minus z0 is greater than R. Now, the fact that R is greater than R2, since R is greater than R2, there exists some n. Now, this n is not dependent on the n taken earlier. This is a new natural number n, such that for all n greater than capital N, the ratio a mod an by mod an plus 1 is less than small r. Because if there does not exist one such capital N, then we would have infinitely many values. Same argument, where mod an by mod an plus 1 would be greater than or equal to r, and therefore the lim sup would be greater than or equal to small r. That would be a contradiction. So this should happen. There exists one such capital N. And this, by rewriting, just tells us that mod an plus 1 times r is greater than mod an. But then we are done now, because our setup is for all those points z such that mod z minus z0 is greater than r. Then what happens is, if you look at a for n greater than capital N, mod an plus 1 z minus z0 to the power n plus 1, this is greater than mod of a n plus 1 times r to the power n plus 1, which is greater than mod of a n r to the power n, and so on, which is greater than mod of a capital N r to the power capital N. And that means that this is the tail, right? The tail is always greater than some constant m. It does not converge to 0. Since the summands don't converge to 0, the series does not converge. summation anz minus z naught to the power n does not converge. What was the z that we picked? The z was that means the set of all z such that mod z minus z0 is greater than r, greater than small r. This is contained in the set of all z such that mod of z minus z0 is greater than or rather greater than or equal to capital R. This just tells us that dz0 r is contained in the set of all z such that mod z minus z0 is less than or equal to small r. I could have just directly written that r is less than or equal to small r. And this is true for all r greater than capital R. Since this is true for all r greater than r1, this implies that r is less than or equal to r1, and hence we have proved it. Hence we have completed the proof of the ratio test. So the ratio test gives us a very handy way to compute the radius of convergence at times. So for example, let's look at a few examples now. Let's look at the example we are familiar with, e to the power z be equal to summation z to the power n by n factorial. Here a n is 1 by n factorial, and if you look at mod a n by mod a n plus 1, for every n natural number, this is equal to 1 by n factorial by 1 by n plus 1 factorial. Let me write it down as n plus 1 factorial by n factorial, which is equal to n plus 1. So if you look at the lim sup and the lim n, both turn out to be infinite. Hence, the radius of convergence is infinite. The exponential, it converges on the entire complex plane. What about the function? What about the power series summation n factorial times z to the power n? So notice that both these examples are power series around the origin. We are now looking at n factorial times z to the power n. Check that mod a n by mod a n plus 1, this is just going to be equal to 1 by n plus 1, which converges to 0 as n goes to infinity. And that means that the series does not converge outside the point 0. Hence, the series converges only at the origin. Let's now look at the familiar example of the geometric series. Geometric series is a power series around 0, and it has radius of convergence 1. So notice that the points for z mod z equal to 1, the series diverges. So you take any point on the boundary of the disk of convergence, the power series here diverges. But let's play around with the geometric series a bit more. For any point in the disk of radius 1 around 0, which is the disk of convergence, we can say that z times summation z to the power n is equal to summation, let me now be careful with the indices. This is just going to be equal to z to the power n plus 1. By rewriting, this is equal to summation n is equal to 1 to infinity z to the power n. Let me just write this as by adding 1 and subtracting it. This is going to be again the same power series minus 1. And by doing the usual algebra on d01, we have summation z to the power n is equal to 1 by 1 minus z. That's quite remarkable because 1 by 1 minus z is a rational function, which we have already seen is a complex differentiable function on c minus 1, isn't it? On c minus the 0 of the or the root of the denominator. Denominator is the polynomial 1 minus z, whose root is exactly at 1. On c minus 1, the function 1 by 1 minus z is holomorphic. In fact, we have already seen that. But then the geometric power series summation z to the power n does not extend past the unit disk. So it's important to note that it can happen that on the disk of convergence, a power series converges to a function which may well extend beyond the disk of convergence. So hence 1 by 1 minus z is a function which extends beyond d01, which is the disk of convergence. Of summation z to the power n. So even though this power series is restricted and lives within the unit disk 1 by 1 minus z, and it converges to a function 1 by 1 minus z, but 1 minus 1 minus z can very well have its existence outside the unit disk. That's something which should be kept in mind. We will return to this later. We saw this example where, however, the power series summation z to the power n does not converge at any point on the boundary. If we tweak the power series a bit, you look at summation z to the power n by n square, this is a power series which also has radius of convergence 1. And now you can check that at the point mod z is equal to 1, the series converges now. So the boundary of the disk of convergence is a subtle place. It can happen that the series converges there. It can also happen that the series does not converge, like we saw in the case of the geometric series summation z to the power n. But what can be said for sure is that if there is one point where the given power series does converge, then the behavior as we approach the boundary point will be nice. And that is the content of what is called as the Abel's theorem. So let me write down the statement and prove the theorem step by step. Let f of z, let's give the power series a name, f of z an z minus z0 to the power n. This be a power series which converges with a positive radius of convergence. Let me elaborate on that. When I say positive radius of convergence, r means that r is neither 0 nor infinite. It is a positive number. And suppose z1 is equal to z0 plus r e to the power I theta. Notice that this is on the boundary of the disk of radius of convergence. Let this be a point such that f of z1 converges. I'm just telling a convergence here. We are not talking anything about absolute convergence. Suppose this converges. Then the conclusion of Abel's theorem tells us that limit as r goes to r minus through inside the disk of radius of convergence. That's what the implication here is. R is going to r minus from values r small r less than capital R of f of z0 plus r e to the power I theta. This is exactly equal to f of z1. So the behavior is controlled in some sense, and that is the content of Abel's theorem. We will prove this theorem step by step, and the proof is by reducing the problem to a simpler case at every stage. So the first assumption is that we may assume that f of z1 is equal to 0. This assumption can be forced. Why is this the case? Let's define, to justify this, define g of z to be equal to f of z minus f of z1. Remember that f of z1 is a complex number, and this is just going to be equal to summation a n z minus, let me call it bn z minus z naught to the power n, where bn is equal to an for all n greater than 0 and b0 is equal to a0 minus f of z1. Notice that g of z has the same radius of convergence. This g of z is also a power series around z0, and it has the same radius of convergence as f. And moreover, if we manage to prove the result for g, if we manage to prove Abel's lemma for g, if limit r going to r minus g of z0 plus r e to the power I theta is equal to g of z0 plus capital R e to the power I theta, which now in this case is equal to 0. If this is true, then limit r going to r minus of what is g of z plus r e to the power I theta, that is just f of z plus r e to the power I theta minus f of z1 is equal to 0, which would imply that the limit as r goes to r minus of f of z plus r e to the power I theta is f of z. So if we prove the result with the extra assumption that f of z1 is equal to 0, then we are still good. We have indeed proved it in the general set. So we may, from now, hence we will be assuming, or hence we shall assume that f of z1 is equal to 0. Let's do some further reductions. We will next assume that we will show that we can assume z0 to be itself equal to 0. We can also assume z0 to be equal to 0. To do that, define g of z to be equal to the exact series, but now not around z0 but rather around 0, summation a n z to the power n, that n is now from 0 to infinity. If g of r e to the power I theta exists and is equal to 0, and suppose limit, this is what we want to show, right? If this is known for such functions g, r e to the power I theta is equal to 0, then let's see whether we can conclude something similar about f. Then g of r e to the power I theta, you should check this is exactly equal to f of z0 plus r e to the power I theta, and the limit as r goes to r minus of this is the same as the limit as r goes to r minus, and we will be able to conclude that this is equal to 0 because f of z0 plus capital R e to the power I theta is 0, and we know that this is equal to 0. So if we indeed prove it for power series around 0, we can translate it and say that this is true for every power series around an arbitrary point. The last final reduction which we will be doing is to assume that, so hence we shall assume that 0 is z0 is 0. We may also assume, let's reduce it to as simple a case as we can deal with. We may also assume that z0, not z0, z0 is already 0, r is equal to 1 and theta is equal to 0. Let's reduce it to this case in one go. To do that, let g of z be equal to summation a n r to the power n e to the power minus I n theta z to the power n. If you notice carefully, this is nothing but f of r to the power f of r e to the power minus I n theta times z. If you look at the radius of convergence of G, the radius of convergence of G is equal to 1. That is something which you should sit down and check, because okay, it is equal to the lim in n going to infinity mod a n to the power minus 1 by n r n to the power minus 1 by n, which is r to the power minus n by n. Remember, r is a positive number and absolute value of e to the power minus I n theta is 1. So this is just going to be equal to 1 by r times the lim in n going to infinity mod a n to the power minus 1 by n, which is equal to 1. So this is a power series which has a radius of convergence 1 and its disk of convergence is the unit disk. And suppose we have proved the result for the case when theta is equal to 0 and r is equal to 1. That would mean that if, so the statement would be now like this: if g of 1 is equal to 0 and limit r going to 1 minus g of r is equal to 0, then limit r going to r minus f of r e to the power I theta is equal to 0. So you should just check that this is exactly the same. And because of all these reductions, we have finally reduced proving the Abel's lemma to the following statement. So enough to show, hence, to prove the theorem, it is enough to prove the following. Let summation a n be a series converging to 0. Then summation a n r to the power limit r going to 1 minus a n r to the power n is equal to 0. This is the statement which we now have to prove. If we prove this statement because of all the reductions, we can see that Abel's lemma has been proved. Let's now try to prove this statement. Careful, this is the sum was missing. The sum a n r to the power n will be equal to 0. Right, so if you look at summation a n r to the power n. Okay, so even before we go about proving that, notice that summation a n is converging to 0. So let capital A n be equal to a0 plus a1 plus up to a n. The fact that summation an converges to 0 means that given epsilon positive, there exists some capital N such that for all n greater than capital N, mod of an is less than epsilon. That is what summation an going to 0 means. Now let's rewrite the partial sum. Let us look at 0 to, well, these need not be the same n, so let me write it as n. A m r to the power m. Let's see how we can rewrite this. This is just going to be equal to a0 is just capital A0 and a1 is a1 minus a0, small a1 is capital A1 minus a0, capital A0 times r plus, going on that way, we have finally capital AM minus capital A m minus 1 times r to the power m. And if we rewrite this, this is just going to be equal to summation a n r to the power n minus r to the power n plus 1, where n is going from 0 to m minus 1 plus a m r to the power m. This is the expression we get for summation am. Oh yeah, it's not am r to the power m that I was writing. It was summation an r to the power n, where n is going from 0 to m that we were writing. So this is exactly what we will be getting. Let us now see what happens when we take the limit as m goes to infinity. The term am r to the power m converges to 0 because am converges to 0. And hence summation n is equal to 0 to infinity an r to the power n is equal to 1 minus r times summation n is equal to 0 to infinity an r to the power n. Of course, we have to now study what happens to the series on the right. We are yet to explore the convergence of this particular object for r less than 1. Did we put the condition that r is less than 1? Okay, we have still not put the condition r less than 1. So for r less than 1, let's see what happens to the right hand side. Consider the RHS. And given epsilon positive, let capital N be such that maybe I should change this a bit and I'll write this as epsilon by 2 just so that I get epsilon at the end. So the given epsilon positive as above, let's see what happens to the right hand side. The right hand side will be 1 minus r times summation n is equal to 0 to capital N a n r to the power n plus the RHS. And then there is a 1 minus r into summation n is equal to capital N to infinity a capital N r to the a n r to the power n. And we know that if you look at the absolute value of this, the absolute value of this is less than or equal to the absolute value of these terms, 1 minus r, which is a positive number, times the absolute value of a n r to the power n, where n is from 0 to infinity, plus 1 minus r times the absolute value goes in, which is mod a n into r to the power n. We can certainly say this. And we took capital N in such a manner that the term mod a n is less than epsilon by 2. I just changed it to by 2 so that I'll be able to write that here. So this is less than or equal to 1 minus r times summation n is equal to 0 to, sorry, not infinity here, it will be capital N. Capital N a n r to the power n plus 1 minus r into, let me put the epsilon by 2 here. And what remains is a geometric series which we know converges to r to the power n by 1 minus r. For r less than 1, we know this, and this precisely is equal to 1 minus r times, we have not addressed the first term yet, we will come to that in a minute, plus epsilon by 2. This cancels off, and remember that r is less than 1, so this is in fact less than epsilon by 2. So the second term is bounded for n large enough. The first term is what we are now concerned about. The function summation n is equal to 0 to capital N a n r to the power n. This is a continuous function, on 0 1, and hence there is an upper bound, there is a bound beyond which this will not go. Hence there exists capital M such that summation n is equal to 0 to capital N a n r to the power n is less than m for all r in 0 1. Let us now pick r so close to 1 that 1 minus r is less than epsilon by 2m. So let r be such that 1 minus r, this is now is less than epsilon by 2m, and then let's see what happens to the first term. Then summation n equal to 0 to capital N 1 minus r times this, maybe I should write it again. Then 1 minus r times the absolute value of summation a n r to the power n, where n is from 0 to capital N. This is less than or equal to epsilon by, maybe I'll put this is a strict less than, doesn't matter though, epsilon by 2m times m, which is equal to epsilon by 2. So for r very close to 1, hence limit as r goes to 1 minus of summation a n r to the power n, this is going to be limit as r goes to 1 minus of 1 minus r times summation a n r to the power n. We just proved by breaking it into two pieces that for r sufficiently close to 1, the sum is this, the thing inside the bracket is less than epsilon, and hence the limit is equal to 0, and that's precisely what we had set out to do. And with this we complete the proof of Abel's theorem. So as noted, the power series behavior, the behavior of the power series on the boundary is a bit subtle, and Abel's theorem is one step in the direction of understanding the boundary behavior of the power series. In the next lecture, we will describe the analytic properties of the power series within its disk of convergence.